Hello students, and welcome to our 9th and final video here for further graphs. We're looking at parametric equations today, which is something kind of new and different. Now, with parametric equations, we introduce a third variable with x and y, usually t, and we describe how x changes with respect to t and how y changes with respect to t. We separate the x's and the y's out and look at how they vary according to some third variable called a parameter. Now, some examples here. A Cartesian equation for a straight line looks like y equals mx plus b. But the parametric equations might look like, not necessarily, they might look like x equals t and y equals 2t plus 1. Right, you can see this is an expression for x in terms of t, and this is an expression for y in terms of t. Right? X and y are expressed independently, but they are still linked by that parameter t. A parabola, again, we have x in terms of t and y in terms of t. And for a circle, x in terms of t, y in terms of t, and because a circle, depending on how we parameterize that, we very often see trig functions pop up there in the parametric equations. So let's jump into an example. Here we have a person who's travelling around a roundabout. Okay, they start at this point here, right, at the positive x-axis, and my parameter t is going to describe the angle formed at the centre of that circle, right, between the x-axis, where we started from, and some point on the circumference, some point P, which has coordinates x, y. So we start here, and we're moving in that direction there. What I want is an expression for the position of this point in terms of t. Okay, well, in terms of t, what are the coordinates of x? If I draw a little right angle triangle here, where t is this labelled angle, then I have a hypotenuse of 1. My adjacent side here is going to be the x-coordinate, and my opposite side here is going to be my y-coordinate. Okay, so that means that, right, if the cos of theta is adjacent on hypotenuse, that means cos t equals x over 1, or x equals cos t. Similarly, sine theta is opposite on hypotenuse, and the opposite is y. The hypotenuse is 1, and theta is t. So that means that y equals sine t. So here is an expression for the point there. It's where x is the cos of t and y is the sine of t. Now what we want to do is to eliminate t from those two parametric equations to produce the Cartesian equation. Very often what we do is make t the subject of one of those equations, one of those parametric equations, and substitute it into the other. That's not going to work terribly well here. It would be terribly complicated if we tried to do that. Instead, what we're going to do, knowing that one is in terms of cos and the other is in terms of sine, we're going to use this Pythagorean identity, knowing that sine squared plus cos squared equals 1. So this means that x squared is cos squared t, and y squared is sine squared t. And if I add those two equations together, and x squared plus y squared is cos squared t plus sine squared t, means that x squared plus y squared equals 1. The parameter has been eliminated from that, and I have a Cartesian equation, which is, of course, a circle with the centre at 0, 0, and a radius of 1. Now, a different example. I have the parametric equations, and I want to find the value of the parameter at some point on the curve. Okay, this relies on that point being on the curve. Of course it will be. So that means that x equals 0. I'm going to replace the x with a 0. And that y equals 2. So I substitute 2 for the y. 2 cos t equals 0 means that cos t equals 0, divided both sides by 2, of course. Means that t is the inverse cos of 0. And between 0 and 360, there are two solutions for that at 90 degrees and 270 degrees. So let's hang on for a moment. Substituting y equals 2 into this parametric equation and dividing both sides by 2, I find sine t equals 1 means that t is the inverse sine of 1, and between 0 and 360 there is only one angle that has a sine of 1, and that's 90 degrees. So the solution must be where t equals 90, because if t was 270, then my y-coordinate would be -2. Rightio. So t equals 90, there we go. We substituted those 2 points in, or sorry, those 2 coordinates into our parametric equations. We're going to create a table of values here from our parametric equations, so for different values of t, and then we're going to sketch this. So, simple enough. If t is -2, x is t squared, -2 squared is 4, and half of -2 is -1. -1 squared is 1, and half of -1 is -0.5. Right, we're just going to push through and fill all of those out. Okay, so I've got a table of values now, a series of points here. Now we only want to look at t is greater than 0, so I'm going to look at these 3 points. Right, here's a pair of axes. There's my first point at 0.25, 0.25. I could have done 0, 0, and just had an open circle. I'll just keep that in mind at the end. So our first point, 0.25, 0.25. Second point should be at 1, 0.5. That should be here. Right, and there's my third point, okay, at 4, 1. Right, I've got those 3 points, and I know it passes down here as well. We want strictly greater than, so I want an open circle there at the origin. And there's my curve through those. And that happens to be a parabola, concave right. Okay. Now, to find Cartesian equations from the parametric equations, what we need to do typically, right, we didn't do it the last time, but we're going to do it this time, make t the subject of one of those and substitute in. So looking at the parametric equation for y, I'm going to change that around, divide both sides by 6. Right, now I've got an expression in terms of t, or an expression for t. I'm going to substitute that into the x parametric equation. Right, so 3 times this squared, right, and I end up with x is 1/12 of y squared. Right, that's a Cartesian equation. Now, that is in terms of x, and we generally prefer it in terms of y. So rearranging that, I get y is plus or minus the square root of 12x. Not a function, but a relation. Here's another one. X equals 1 minus 1 over t, and y equals 1 plus 1 over t. We're going to make t the subject of one of those. So let's find an expression for t in terms of x, because then when we substitute through, y will already be the subject. So looking at this one here, what I'm going to do is multiply everything by t. So I get xt equals 1 times t minus 1 over t times t, it's just minus 1. Okay, now I'm going to add 1 to both sides, subtract xt from both sides, or tx, factorize that, and I end up with t equals 1 over 1 minus x. Seems like a fair bit of work, and there's still a bit to go. Now what we're going to do is substitute this in, right? We're going to replace t in the parametric equation for y. I'm going to replace t with this expression here. Okay, you can see that's what I've done there. I replaced the t with 1 over 1 minus x. And as I expand, rearrange that, we know if I divide by a fraction, it's the same as multiplying by its reciprocal. Okay, and when I do that, I end up with y equals 2 minus x. It certainly seems like a very simple equation there for some fairly complex parameters. Okay, that's how it goes sometimes. Righto, there was a fair bit going on there. That's the end of it all. I hope it made sense. parametric equations, the main thing I really need you to be able to do is to find the x and y coordinates given the parametric equations, right? Given a parameter, right, and the parametric equation substituting to find the x and y coordinates. Alternatively, I might find the parameter by substituting x and y into those parametric equations. And I'm certainly going to ask you at some stage to find a Cartesian equation from the parametric equations, right, by eliminating t, by combining those two equations together. Okay, that's all. That's the end of further graphs. Hope it was good. If you've got any questions, make sure you ask me in class. Thank you.